Hey guys, hope you're doing well. I know you're excited to further our understanding in quadratic equations, particularly graphing them in vertex form. But before we begin, let's review a few things. Here I have f of x is equal to x squared. This is the parent function. Everything outside of x squared is a transformation, and we're going to get into that in detail very shortly. So if you don't remember how to graph y is equal to x squared, the easiest way is to make a table of values. Now we can choose any value of x because the domain of any quadratic is all real numbers. But in this case, I'm just going to use -2, -1, 0, 1, and 2. Now I'm going to take these values and substitute that into my value of x to find out what my value of y is. So I have f of -2 is equal to -2 squared. -2 times -2 is +4. Again, I'm going to do that one more time for you. F of -1, -1 squared, and that gets me 1. If I substitute 0, I get 0, 1, 1, 2, 4. Now I'm going to plot all these points. -2, 4 is about there. -1, 1, 0, 0, 1, 1, and 2, 4. Now, hopefully you remember that the minimum or maximum is the vertex. This is a minimum because it is the lowest point, and that is at the point 0, 0. We also can see that we have an axis of symmetry, which cuts the graph in half and goes right through my vertex. Now let's take a look at the other equation. F of x is equal to -x squared. Again, I'm going to start with my table of values. I'm going to choose the same values, -2, -1, 0, 1, 2. F of -2 is equal to -2 squared. -2 squared is +4. Negative times positive is at -4. Now, completing the table, I get -1, 0, -1, and -4. And now I'm going to plot these values to see exactly what happens. -2, -4 is about there. -1, -1, 0, 0, 1, -1, and 2, -4. And now you can see that there is a reflection over the x-axis. And I now have a maximum as my vertex. And this is still at the origin, 0, 0. The axis of symmetry is the same at x is equal to 0. Now we have a few more examples to go before we continue into vertex form. So here is a little bit different. I have x squared minus 3, and I'm going to evaluate them at -2, -1, 0, 1, 2. So let's do the first one. F of -2 is equal to -2 squared minus 3. -2 squared is 4, minus 3 is 1. So my first point will be at -2, 1. The second point, doing the same exact thing, will get me -2. 0, -3. When I substitute 1, I get -2, 2, and 1. So I'm going to plot these points right now. You can do the same in your notebook. -1, -2 is about there. 0, -3, 1, -2, and 2, 1. I'm going to connect these dots. roughly, right? So, what do we notice? If you remember, my original, or my parent function, looks something like this. Because I'm subtracting the -3, I have a vertical shift down. 1, 2, 3, 3 units. This is going to come in handy later on. Now let's take a look at the next equation. Again, a little bit different. So we're going to go ahead and evaluate for each of these values. F of -3 is equal to -3 plus 2 squared. -3 plus 2, -1 squared, giving me +1, excuse me. When I evaluate the function for -2, f of x is 0, -1, 1, 0, 4, and 1, 9. So just like the last three, I'm going to go ahead and plot these points. -3, 1, -2, 0, -1, 1, 0, 4, and 1, 9. Just a little over. So I'm going to connect my dots. Great. Now, this is where the axis of symmetry can help us with the left side of this graph. So again, the axis of symmetry goes right through the vertex, which happens to be -2, 0. And the axis of symmetry is x is equal to -2. Knowing that the point is 3 units to the right, I could then use the information that I know about symmetry to get my last point. If I move 3 units to the right, I must move 3 units to the left. And now I can complete my graph. And we're going to pretend that those are connected. Great. Now let's see what happens when we tie it all together. Here are the 4 different graphs that we have discussed so far. Now, what happens when we combine them? As such, this equation is actually in vertex form. We're going to get into the formal definitions and we're going to dissect this a little bit later. But right now, let's just look at what happens to my vertex. If you recall, we said the original function, also known as the parent function, is y is equal to x squared. However, when we added a negative in front of my x squared, that gave us a reflection over the x-axis. When I subtracted 3, that shifted every single point down 3 units. And when I added x plus 2, that moved my graph to the left. Now, if you're wondering, why did I move it to the left when it's +2? Well, we're going to get into that very soon, but just hang tight. So I want you to focus your attention on the vertex of my parent function at 0, 0. When I had this reflection, the vertex, if you recall, was exactly the same, 0, 0. However, when I subtracted 3, I moved down 3 units, being right about there on my graph. And this gave me a translation, or a horizontal shift left 2 units, bringing me to this point. So I started here, my parent function. I went down 3 units and left 2 units because of this equation. And this is why this equation is so important. Now, let's not forget we had a negative. So taking this point, I'm going to roughly draw my equation, the graph of my equation, and there you go. Again, today, all we're learning about is how to draw a rough draft of a parabola, given its equation in vertex form. So, let's take a look. Again, I like to start with a textbook definition because it's important to understand terminology. At this time, you may pause the video so that you can have enough time to take these notes and resume as soon as you're done. Great. Now let's break it down just a little bit more. So you have the equations and the description, but you might not understand exactly what each section means. So we're going to break it down. Let's take a look at this value of a. When a is greater than 0, then the graph is going to open up, like so. But if a is less than 0, as you saw in our second example, we had a reflection, so my graph is going to open down. And HK happens to be the vertex. And again, the x value of the vertex is the axis of symmetry. Now, when I have x minus h in my parentheses, this translates the graph right. And if I were to have x plus h, that translates it left. When I say translate, I'm really just saying to shift. Now a shift can be left, right, up, or down, as you saw in the last 4 examples. Now, let's take a look at what happens when a is a number other than 1. Well, when a is greater than 0 but less than 1, the graph is a vertical shrink. And if a is greater than 1, the graph is a vertical stretch. We have a few more examples to show you how this ties in to an equation and its graph. So let's take a look. This is my quadratic equation in vertex form. Now if you noticed on the top right, I have my parent function y is equal to x squared. However, every time I add a new value, a, h, or k, the graph will change. And so a, again, if it's greater than 1, it gets skinnier or narrower because of that vertical stretch. And if a is greater than 0 but less than 1, then it is a vertical shrink, or it gets wider. And like you saw in our previous example, if a is negative, it opens down, like you see here. And if it's positive, it'll open up. Again, taking a look at what happens when h has a value, we saw that there was a horizontal shift left 2 units. And when k had a value, it went down 3 units because that k was negative 3. So let's see what that looks like